Okay, hello everyone. So, as per last video, we're going to press on with Laplace transform series. What we're going to be discovering today is Laplace transform of t to the power of n. And the reason why I'm doing it that way is because it's just a nice generalized form, and really you find it's very repetitive, so you may as well discover all the options for an exponent, a numerical exponent of t. And what this is going to be is integral from 0 to infinity, or the improper integral, shall I say, of that. And then, yeah, we just do it as we often do. We do it by integration by parts, which means preferably the exponential function is going to be v, and the function we want to reduce is going to be u. And then doing things that way means that we have a form here of and some people for some random reason prefer writing it as this. I think it's just because they generally like the integral notation when they're defining a formula to help people integrate, which makes sense, but it just makes you have to do extra work here with the integration of v prime, so I prefer it this way. So yeah, I'm going to stick to this. Okay, so then hopefully we'll manage to do this in less than 10 minutes, because my other videos are getting really long. Okay, so what we have here is minus 1 over s, e to the minus s2, st, sorry, and then times, this is untouched, but then we have to integrate t and prime, t to the power of n, all of that prime, so then we just apply the regular power rule. There's no difference, it's just that this is a generalized form. Okay, minus 1. And then we know that this is going to generate this here. It's the same function. So we just add reciprocal of s. And then we just transfer this constant here to here, just to make things more neat. And what do we end up having? We end up having, sorry for the background noise, but there's always got to be something, I guess. Yeah, whether it's nighttime or like early in the morning, there's always going to be something. Okay, so we have what this started with, pretty much, and then thus n over s. And what do we have here? What do we have here? It looks messy, so I'm just gonna show you. This is basically the shifted version of what we were trying to figure out in the first place. So it's like finding the Laplace transform of t to the power of n minus 1, which is very useful. In turn, you can present it as this. Now we're just going to split this into two parts, because it's impossible to work out the improper integral when you already have this kind of primordial Laplace transform, which you don't really know. So yeah, it's just gonna cause an infinite loop. So I'm gonna break the infinite loop by doing them separately. So limit as a approaches infinity of this thing over here. And what we have here is, we already know, but we don't need to discuss it again, but this is going to be 0, because as t approaches infinity, the result of this gets infinitesimally small. So that's going to be 0 times this, which diverges less quickly, because it's not a function of e. It's not a function with a particularly high divergence rate. So we're just gonna say it's 0, because it is 0. and you can check it using a calculator. Just if you don't have a particularly advanced calculator, just gradually increase the value in brackets, and you see that's what you get when t approaches infinity. And now we are comparing this with the result we get for 0 for when t equals 0. What we find is that it approaches. We find it approaches. Well, here it would be 1. So that is minus 1 over s times 1, but then t is equal to 0, so you just cross out the whole thing. It's 0 equals 0. And then we're just comparing this to the other integral we have here. So here we just end up having 0, right? There's nothing interesting about it, about this whole thing here. So we just move on to this. And what is that? Well, n is not some crazy little thing. It's a number, right? All we need to do is just choose. We need to choose a number. So I'm just gonna say, okay, I want to find t to the power of 2, t squared. So we know that this over here, should be n over s times the Laplace transform of t to the power of 1. T to the power of 1 is t, right? Yeah. And that is, the brackets are really difficult to draw when you're doing it in real time. And we already reviewed this. Sorry, just looking at it. We already did this in the previous video. I think it was the first video I had here in this series. And we know that is 1 over s squared. So then I can confidently say that Laplace transform of t squared is going to be n over s times 1. Well, 2 s squared. Yeah, this is 2. Yeah. Okay. I was thinking about a generalized form. Didn't really get to do the particular case. So I'm just going to do it now. So then 2 over s times 1 over s squared. Yeah, that's you get. And that's just, I'm not gonna show you like the generalized form now. I'm gonna let you realize it by doing another one, and that's gonna take me like 10 seconds to just watch. We'll just kind of shift this here. We'll just carry it on to the next Laplace transform we're solving. Yeah, the cubic version. So then that's just going to be the same value as the result of a previous Laplace transform times this. And what do we have here? What we have here is no less than 3 factorial over n plus 1, or n plus 1 as an exponent of s. Yeah, I thought it's just quite cool, because normally when people think about factorials, they think, oh wow, that's a completely human-made function. Of course, in nature, you don't have numbers just randomly multiplied by the numbers before them, because that's a very human thing to think about, like how we have our own number set and which number comes first and all that stuff. But the factorial, just showing it here. The factorial is very interesting, and it's really cool, in my opinion at least, to see how you can actually derive something and end up having a factorial, simply because you're multiplying some number or some expression by the previous one. and over time it kind of accumulates to this factorial. So I think it's interesting. So yeah, that's it for today. I try to stick to 10 minutes. It's roughly, it's more than 10 minutes, but yeah, I don't have any proof or anything. It's just to get you kind of understanding this, because it's a very important entry in the Laplace transform in the lookup table, because you can use this to work out pretty much any polynomial, because we know that, well, we don't know, we're going to show that Laplace transform is linear, so that means that using this property, you can just take any polynomial and solve it step by step, and then get a result like this, which is very useful. Then it will also become useful in inverse Laplace transforms. So this is a foundation, guys. So I hope you enjoyed it, and see you later.